Hello guys, in this video I am going to present a tutorial on branch and bound method. Branch and bound method is one of the methods to solve integer programs. In this video we are going to take an example and see how the branch and bound method works. Specifically, we are going to see some of the strategies that we can use in exploring the branch and bound enumeration tree. This is the example that we are going to consider in this tutorial. The objective is to maximize a linear function subject to a linear constraint, and we have binary restriction on domain. We are going to see three different combinations of node selection, branch selection and variable selection, and these combinations are called as strategies. So we have the first strategy wherein the node selection is best bound. Best bound is also called as best first or best parent bound. The idea here is to select a node whose parent has the best bound. The branch selection in this strategy is branch up, or in short up. The idea here is whenever you have two branches to select from, you go with the branch up side. That is nothing but the greater than or equal to side. In the variable selection, we have highest fraction. What it means is if you have more than one fractional variable, then pick the variable that has the highest fraction. So let us see how to implement strategy 1 in the branch and bound tree. The branch and bound tree begins by solving the root LP relaxation of the integer program. Here is the integer program and the corresponding root LP relaxation is here. You can see that the only difference in the root LP relaxation compared to the original integer program is the restriction of domain. In the original problem, all the variables are binary, whereas in the LP relaxation, the variables are continuous between 0 and 1. Now this node here represents the process of solving the linear program. The number here represents that we are solving the first linear program. When I solved this linear program, the optimal objective function value was 10.8. and the only fractional variable that I had in the solution was x2. All the other variables were either 0 or 1. Now because we solved the root LP relaxation, what we have is the best bound on the integer program. And the objective function type is to maximize. So the bound will correspond to the upper bound. Notice that the objective function value contains only binary variables and the coefficients are all integers. That means the optimal solution to the original integer program can never have a fractional value. Therefore, the upper bound can be further improved to 10. Now, since x2 is the only fractional variable, we are going to branch on x2. We will have two branches, the branch up side and the branch down side. The branch up side corresponds to x2 greater than or equal to 1. And for binary variables, x2 greater than or equal to 1 is same as x2 equals to 1. Similarly, the branch down side corresponds to x2 less than or equal to 0. And for the binary variables, x2 less than or equal to 0 is same as x2 equals to 0. Now we have to pick from these two branches one of the branch. And the branches are selected based on the branch selection strategy. So in this strategy, we have the branch selection as branch up. That means I am going to solve the LP that is generated here first. So let us see the LP that is generated here. The LP that is generated here will have the same objective function, the same constraints like that of node 1, except that we have one additional constraint which corresponds to the branch. When I solved this LP, the optimal objective function value was 10.5 and the only fractional variable in the solution was x3. Now we have 3 LPs that are generated and we need to pick one of those LPs to solve. One of the LP will be generated here or 2 LPs will be generated here. So we have 3 open nodes. To select one of the nodes from either A or the group of B and C, we are going to use the node selection strategy. The node selection strategy here is best bound. So now we can see that node A's parent, which is node 1, has the best bound compared to node B and C's parent. Therefore, we select node A and investigate. This is the LP that is solved at node number 3. The LP has the same formulation like that of the parent node, except that the branch constraint is being added to the LP. So the only additional constraint that you have in node number 3 is x2 equals to 0. Notice the numbering. The LP that we solved first is marked with number 1. The next node is marked with number 2 and the third node is marked with number 3. So this shows the order of processing the nodes. When I solved the LP at node number 3, the optimal objective function value was 10.8 and the only fractional variable was x5. Now we have 4 open nodes to select from. We have 2 nodes from here and 2 other nodes from here. According to the node selection strategy that we have, we are going to select one of the nodes from this group because 3 has the best bound compared to 2. Now from these 2 branches, we are going to select the branch up because of the strategy and we are going to solve the LP at node 4. Here is the formulation of the LP at node 4. As you can see, compared to the parent node, the child node has one additional constraint which is coming from the branch. When I solved this LP, the optimal objective function value was 10.64 and the only fractional variable was x4. I have one open node here, 2 open nodes here and 2 open nodes here. From these, based on the best bound, I will select this node to process. When I solved the LP at node number 5, the objective function value was 10.33 and the only fractional variable was x1. Now I have 2 nodes from here, 2 open nodes from here and 2 open nodes from here. And based on the node selection strategy, I am going to select the 2 nodes from here to process. From these 2 branches, we are going to select the branch up. That is part of the strategy. And when I solve the LP at node number 6, the optimal objective function value was 10.6 and the only fractional variable was x3. Now among so many open nodes, the next node to solve based on the node selection strategy will be this one. And when I solve this, the optimal objective function value was 9.67 and the only fractional variable was x1. Now from so many open nodes, the node with the best bound is node number 6. So I am going to investigate the childs of node number 6. From these 2 branches, branch upside will be selected. And when I solve the LP at node number 8, I found the LP has no feasible solution. So this node will be killed and I'm going to write a small label next to it, NFS, which stands for no feasible solution. So this node is the dead node. I don't have to investigate the childs of this node. The next node based on the node selection strategy will be this one. And when I solve this node, the optimal objective function value was 9.67 and the only fractional variable was x1. So now we have so many open nodes. 2 nodes from here, 2 from here, 2 from here and 2 from here. Among all the open nodes, the nodes over here has the best bound. So we are going to investigate node number 2. From these 2 branches, we are going to select the branch upside. And when I solve the LP at node number 10, I found no feasible solution. So this node is killed by the label NFS. The next node based on our strategy will be this node, and when I solve this node, the objective function value was 10.5 and the only fractional variable was x4. Among all the open nodes, we see that this node has the best bound, so I am going to investigate this node further. We are going to select this branch because it's the branch upside, and when I solved the LP at node number 12, there was no feasible solution. Just a quick reminder, the LP that we solved at node number 12 has the same constraint as the LP at node 1 plus x2 equals to 1 plus x3 equals to 0 plus x4 equals to 1. So compared to node 1, it will have 3 additional constraints. Compared to node 2, it will have 2 additional constraints. Compared to node 11, it has 1 additional constraint. The next node in line to solve will be this node, and when I solved the node, I found the objective function value was 10.4 and the only fractional variable was x5. From all the open nodes, this node has the best bound, so I am going to investigate the childs of this node. Among these two branches, I am going to select the branch upside first, and we have no feasible solution at this LP. Now the next node in line based on node selection strategy will be this node, and when I solve the LP here, the optimal objective function value was 9, and I found that all the variables were integers. So I have an integer feasible solution, and this node is killed, and the label I am going to use now for this node will be IFS. It means integer feasible solution. Remember, a feasible solution will give you the worst bound, and since the objective function is to maximize, it will be the lower bound. At this point, if you would like to terminate the branch and bound tree, then you can conclude that the integer solution that you found is within 10% of error from the best possible solution. You can see that the best possible solution has a value 10 and the current solution has a value 9. Since this is the only integer feasible solution, we can say that this is the best integer solution so far. And the best integer solution so far is called as incumbent solution. We are not going to stop here. We are going to stop until we found that the percentage error is 0. Now among all the open nodes, 2 from here, 2 from here, 2 from here, the best bound is coming from node number 5. So I am going to investigate the childs of node number 5. From these two branches, I am going to select the branch upside, and when I solve the LP here, the optimal objective function value was 9.33 and the only fractional variable was x4. Now we'll solve the next node in line, and the optimal objective function value at this LP was 10 and all the variables were integers. So I give it a label IFS, and this node is dead. So I don't have to investigate any further. Now notice that with this new information, the lower bound has moved from 9 to 10 and the percentage error is 0. So we have reached the optimal solution. In fact, all the open nodes that we have here are now dominated by this incumbent solution. We have these two integer feasible solutions, and the best of the integer feasible solution at any given time is called as incumbent. So all the open nodes now are dominated by this incumbent solution. It means if I do the processing of node 16, the best integer solution that I can get from here will be 9, and I already have something better. Similarly, if I do the processing of this node, the best I can hope to get is 9, and I have already 10. So these nodes are dominated by node 17. So I can kill these nodes with the label DIS. It means dominated by incumbent solution. Dominated by the incumbent solution. So now you can see that all the leaf nodes of the branch and bound enumeration tree are dead. That means we have the optimal solution at hand, which is obtained at node number 17. In the next slide, we'll see how the same problem is solved with a different strategy. The difference here is in the node selection, we have depth first, best back. Depth first, best back sometimes is also called as depth forward, best back. The idea here is you solve the most recent node until you hit a dead end. And from there you pick the best node available in the tree and proceed. In the branch selection, we are going to use branch downside, and in the variable selection we have lowest fraction. So let us start the branch and bound tree. We solve the first LP. Here is the optimal solution and the corresponding fractional variable. Notice that in all the LP problems that we have so far, we always end up with one fractional variable. The reason is the knapsack style constraint that we have. So basically the variable selection strategy is never used. However, if you have more than one constraint, then you might have multiple fraction variables popping up, and from that, if you would like to select one of the variables to branch, then we are going to use this variable selection strategy. So now I am going to select from these two branches this branch, and the node here will be processed. The optimal objective function value of the LP at node 2 was 10.8, and the only fractional variable is x5. Since it's the depth first strategy, we are going to solve the child of node 2. From the two childs, I am going to select this child because of the branch selection strategy, and the optimal LP objective function value was 10.33, and the fractional variable was x1. Since it's depth first, I am going to select one of the childs of node 3, and because of the branch selection, this child will be selected. And when the LP at node 4 is solved, the optimal objective function value was 10, and we found an integer feasible solution. Now with this information, search I will be doing at these nodes will not have a better solution than 10. That implies all these nodes are dominated by node number 4. This ends the branch and bound tree, and we have the optimal integer solution. You can see that changing the strategy will have huge effect on the size of the enumeration tree. We have found the same solution, but the tree here has less number of nodes compared to the previous tree. Now let us solve the same integer program using a different strategy. This time we have for node selection breadth first and best next. What it means is I solve all the nodes in the same level before I move to the next level. And inside the level, we are going to select the best node and process. Branch selection is branch up, and the variable selection is nearest to integers. Similar to the previous strategies, first we are going to solve the root LP relaxation, and we have the objective function value and the corresponding fractional variable. Then we branch on that fractional variable. From these two branches, based on the strategy, we select one of the branch and create the LP. When I solved LP at node number 2, that was the objective function value and the fractional variable. Based on the node selection strategy, I am going to solve this node first before I consider the childs of node 2. When I solved node 3, this was the objective function value and the fractional variable. Now I have 4 open nodes. In order to select one of the nodes from these open nodes, I am going to use the best next part of the node selection strategy. So this implies that the childs or the nodes here will be select because node number 3 has the best bound. From these two branches, this branch will be selected first, and when I solve the LP here, the optimal objective function value was 10.67, and the only fractional variable was x4. The next node will be here, and the optimal objective function value was 10.33, and the fractional variable is x1. Now before considering the childs of node 5 or node 4, I am going to solve the childs of node 2 first because of the breadth first strategy. When I solved the childs of node 2, this is what happened. The LP here was infeasible and the LP here gave me optimal objective function value of 10.5 and the only fractional variable was x4. From these three open nodes, I am going to select node number 4 because it is the best next node. And when we solve the childs of node 4, this is what we obtained. The best next node will be node 7, and when we processed node 7, this is what we got. The next best node at this level is node 5, and when we process the childs of node 5, this is what we got. Now you can see that with this information at node 13, which has the objective function value of 10 with the integer feasible solution, all the open nodes will be dominated and they will be killed by the DIS label. So all the open nodes are dead, and we can conclude that the optimal objective function value of the original integer program is 10, and the LP solution here will be optimal solution for the original integer program. Well, that is all what we have in this tutorial. Bye bye.